Okay, you guys. It's pretty daunting to be the one person between you and 10 days of bliss. But I'll do my best. Come on, you can do it. You can get it right. No? I know, you're already on the bus. No, that doesn't look good. That looks better. Awesome. Okay. Today we're going to talk about parametric surfaces, which is sort of the last prerequisite thing that we need in order to talk about the Marquis theorems, divergence theorem, Stokes theorem, that we'll talk about when we get back. Before I do that, questions on the homework? I know you're going to kill the person that asks a question on the homework, right? Is that how it is? Hey, I can stretch this thing out. Seriously, no questions? Andy?
The one that has it's like a slice of a circle in a field.
Yeah, okay. It's either that one or, oops.
Yeah, this one.
Got it, okay. All right. So the idea is, let's see, we want to do, not sure, yeah, we're doing the circulation. So the circulation is F dot dr, if you haven't figured that out already. Okay. So F dot dr is the one where you're doing the curl of F dotted with K, that area integral, yes? So you would compute the curl of F and dot it with K. I'm not going to do that in my head. I'll do it in a minute. You would compute the curl of F, dot it with K, and then integrate it over this region. Maybe it comes out to a constant.
Because you can just do the qx minus, or
yeah, it
qx
looks.
minus py.
It looks like
like 3 minus -4.
So what I predict happens here, Andy, is it comes out to a constant. So then you're integrating a constant over this area, and it's really a matter of just finding the area of that sector. And the area of that sector is the angle at the origin, which is pi over 6, times the radius squared. 16 pi over 6 would be the area of the thing, and then times whatever you get out of that. Go ahead.
A question for number 6.
Okay.
Yeah, the first one.
It looks worse than it is.
I know, it turns out to be like
I kind of just got
0.
frustrated.
So part A?
Yeah.
Yeah, part
the
A.
First one, I did all the rest.
Yeah, part A, it's not that bad.
It goes away, it's just obnoxious.
Yeah, so it looks like a nightmare, but I promise you that if you treat this as, say, f sub x, right? When I anti-differentiate this with respect to x, I have 5yz sitting here and a 5yz sitting here. It goes away when you anti-differentiate. And the same thing happens here. I have when I anti-differentiate with respect to x, I've got the z squared here and the z squared here. Actually, a 2's, I don't know. Anyway, it goes away. So I promise you that if you just write it down and do it, it's not that bad.
Doing the curl too, like you do the cross product.
Yeah, it cancels out.
Yeah, the curl again
It's
is,
still obnoxious to write it down though.
yeah. So
It's long, but then it's
you're going to see that a lot, I promise you, in the next 3.5 class periods. You're going to see these expressions that look like absolute nightmares. And yet, if you use the theorem correctly, the nightmare goes away. So just be warned that that's not the last nasty expression that you're going to see that isn't as bad as it looks. Other questions? Okay. The few, the proud, the 230 Calc 3 people. All right. So, why parametric surfaces? Let me answer that first. All right, this is a bit of foreshadowing about where we're headed. But we've seen in 2 dimensions, in 2D, for example, this integral, f dot dr, is the circulation. In fact, let's not do f dot dr, let's do the other one, f dot n ds. It's a little bit easier to visualize. So what that is you've got these normal vectors to the region all the way around, and then this region is in the presence of some kind of vector field. And the vector fields, there are vectors everywhere, say. But what we're really interested in is the dot product of these force vectors with the normal vectors all the way around. And the big theorem is, the big theorem for this guy is that this is just the integral over the region D of the divergence of f dA. All right? So this involves a line integral and a double integral. A line integral and an area integral. Okay, what we want to do is take this idea and lift it up 1 dimension. So if I take a region, a 2-dimensional region, and turn it into a 3-dimensional region, what happens to its boundary? It becomes a surface. So I take a 2-dimensional region and now I'm going to talk about a volume in space, a 3-dimensional volume in space. Its boundary is a surface. And let's say a closed bounded volume. A closed bounded volume in 3D has a surface as its boundary. Now, what I'd really like to do in particular, I'd like to take this guy and write it like this. I'd like to take a surface integral and turn it into a volume integral, or vice versa. Take a volume integral and turn it into a surface integral. This is called the divergence theorem. This is where we're headed. We know how to do integrals like this. We spent some time doing that. What we don't really know is how to do integrals like this. How do we integrate over a surface? And that's what today's stuff is about, how to integrate over surfaces. In fact, it's a 2-part lecture. So today we'll talk about some preliminary stuff, and then Monday on your return, we'll finish it off with surface integrals. And it's all with an eye towards the divergence theorem. So if we want to do integrals, so to do a surface integral, we need a way of representing surfaces. Whoops. Now, we have ways of representing surfaces already. Up till now, we represent a surface as a function. Z equals but this is limited. How is this kind of representation limited? There are certain kinds of surfaces that we can't represent using this kind of notation. Does anybody know what they are?
movies.
Certainly that's true, yes. Less exotic.
Those that don't pass the vertical line test.
Yeah, is that what you're going to say, Nick?
Yeah.
Yeah. Anything that doesn't pass the vertical line test can't be represented like this, because this is, after all, just function notation, right? Z equals f of xy. You plug in an xy value, you get out a z. You get one and only one z. So any surface that has two z's above a particular point in the xy plane, you can't do it this way. And there are lots of surfaces like that. Spheres, for example, are probably the canonical example, but I'm going to show you some other surfaces today as well. So what we're going to do is we're going to develop a notation and a way of dealing with surfaces that removes this limitation. We're going to use what are called parametric representations. Okay, so if we use parametric representation, all right. Now, what I want to do to motivate this is, let's recall, gosh, I don't remember. I think it was chapter 13. Remember space curves? Okay, recall space curves. We would write them as a function of t, and then each coordinate, x was a function of t, y was a function of t, and z was a function of t. I know it's been a while since you thought about this, but what kinds of geometric figures could you trace out with this? Well, you would trace out essentially trajectories. Like, you would imagine a little particle moving through space, and the trail of that particle would be one of these space curves. That geometric figure of a space curve is a one-dimensional figure. What makes it one-dimensional is, there are different ways of thinking about it, but what makes it one-dimensional is the fact that to describe where you are on that geometric figure only takes one piece of information, t. Right? So I know precisely where I am. If I give you a t, you can tell me where I am. And that's one number, one dimension. What we want to do is generalize this, not by much, but we want to start thinking about surfaces by adding another variable. So now, instead of x, y, and z being a function of a single variable t, we're going to let x, y, and z be functions of two variables, u and v. And just like the space curve could travel through space and sort of loop around and do all kinds of stuff, and it didn't have to be a function or anything like that, surfaces are the same way. This kind of representation lets the surface be a sphere, lets it loop back on itself, lets it be a Mobius strip. It can do lots of stuff. Much more generally than z equals f of xy. All right, let's look at an example here. So let's consider this parameterization and see if we can figure out what it actually is. All right, so R of u and v is this vector v cosine u, v sine u, v. So the x-coordinate is described by v cosine u, the y-coordinate is v sine u, and the z-coordinate is just v. So we have a claim of a helix, a brave person putting himself out there. Let me talk about how you figure out what this is, and then we'll see if we agree. So the way to figure this thing out, the way to figure out what this shape is describing, and it doesn't work for all shapes. Obviously, if I put some monstrosity up there, like, for example, that thing or something like it, you're done. You just got to plug it into a computer and hope for the best. Okay? But, and that's not a surface, that's a vector field, I know that. But I could put something equally messy up there that would be a surface. But for simple, straightforward kinds of parameterizations, there are some thought experiments that you can go through to help you reason out what the surface should look like. And that's what I want to describe for you and get in your head so that when you're doing these exercises, you can sort of visualize some of the surfaces. So fix V and let U vary. What that does is it gives you what's called, this gives what's called a U parameter curve. So let's fix a V, and just to be really concrete, let's fix V to be 1. Then what does R look like? Well, R of U and 1 is cosine U sine U 1. Well, what is that? It's a space curve, right? Because now it only has one parameter, U. So it's a space curve. What does it describe? It's a circle, and where is it? It's a circle of radius 1. Where is it? It goes around the z-axis at a height of 1 above the xy plane, right? There it is. Okay, so once you've figured out what one of these U parameter curves looks like, now what you want to do is let V move. So you understand what the curve looks like for one particular value of V. Now just let V move a little bit. What happens if V is 2? It's at 2 with radius 2. So it went up and it got bigger. Even more information, right? So now you can kind of see, for example, when V goes above 2, the circle gets bigger and it gets higher. So what you suspect is going on is something like that. What happens when V gets small? It goes towards 0. It gets lower and a smaller radius, so in fact it's going to pinch all the way down to the origin here. What happens when V becomes negative? Now you're below the xy plane. Same cone, the opposite direction. Should I be nervous? For example, let's let V equal -1, R, U, -1. Is there any reason to be nervous about having a minus cosine U minus sine U -1? I mean, what is that?
It seems like it would make the same circle, but it would like make it in the opposite way.
That's all it is, yeah. It's the same circle, it's just, right, think about the circle as, right, there's a circle and there's a vector. The normal circle, the vector goes around like this, right? If you multiply, if they're both negative, what happens to that vector? It points the exact opposite direction, right? And then I'd have to think hard about it. I don't know if it would go this way or the other way, but hold on, I can think about this. So it would bounce here. So if it was here, it would go here. So yeah, it's going to still go counterclockwise. Okay, it'll still go counterclockwise. It's just going to start over here and then go around. Does everybody see that? Okay, so no reason to worry about negative v. Okay, well, there's no reason to pick on v. You could do the same thought experiment. So let's fix u and let v vary. And I guess just for the heck of it, let's let u equals 0. Then r of 0 and v is 1, sorry, not 1, v, 0, and v. And this is a v parameter curve. V0v. What does that describe? As you let v vary, what does it trace out? A line. In fact, we know a lot about that line. That line lies in the xz plane, yeah? And it's, in fact, it's x equals z in the xz plane. Okay. So let's see here. This is x, this is y, this is z. So it's perhaps this guy right here. Yeah? Now what happens as I move u around? For example, what if I make u equal to pi over 2? Zero VV? Yeah? And that's a line in the YZ plane? Same line? So what we see is two different ways of thinking about this surface. You can think of this surface as being swept out by circles that grow in radius and rise above and go down below, like that. Or you can think of this surface as being swept out by lines, right? Two different ways of thinking about the same geometric object. So these V parameter curves are really useful to think about. They provide a lot of information about the surface. U and V parameter curves. We're going to see them again in a second, but what I thought I would do is show you a tool that I found online in case you're trying to visualize a particular surface. So there's a really nice Flash application that lets you plot parametric surfaces. And there's obviously a link on the web page here. You might not have thought of it, but a cylinder is a nice parametric surface. Let's think about the cylinder. So the program here uses S and T instead of U and V. But other than that, it's exactly the same. So we have x as a function of s and t, y as a function of s and t, and z as a function of s and t. They're a little bit weird because x and y don't depend on t, and z doesn't depend on s. But that's perfectly okay. All right, let's think about this thing. Let's look at S parameter curves. What are S parameter curves? That's where you fix t and let s vary. So what are the S parameter curves? They are circles, and they're these horizontal cross sections, right? And really the height just depends on whatever fixed value of t that you've used. Okay, what are the T parameter curves? Lines, they're vertical lines, right? And in fact, the software actually relies on this idea to render the surface for you. The software is taking advantage of this way of constructing surfaces. The software just, I don't know what order it does it in, but I can describe for you with fairly great certainty how this thing works. It's going to start here at t min, so start here at 0. And it's going to plot that parameter curve, which is a circle, right, of radius 1, and that's this guy right here. And it's going to increment it. Maybe it's 0.1, so let t equal 0.1. That gives me this guy, 0.2, 0.3, 0.4, all the way up to 3. T max is 3. So it does that big stack of circles in space. Then it goes back and it does the opposite. It starts here at S min, and it sets S equals 0, and then it plots a range of t's. And I'll just say for right here, it gives you that line. Then it increments S. Maybe S is now 0.2. It does this guy, and this guy, and this guy, and this guy. So those grid lines are generated in exactly the same way that I described to you about how to think of these things. S parameter curves and T parameter curves. We can look at our cone if you'd like. We could put a T in front of there. And let's see, we do like 0 to 2 pi, but what we don't like, we'd like to have -3 to 3, say. And there's the cone parameterization that I just was talking about in the notes. Same thing though. Fix a V, fix a T, and plot that circle. And then the next T, plot the circle, and the next T, plot the circle. Then fix an S and plot that line, and then the next line, and the next line. And then have some kind of coloring scheme. Go ahead, Greg.
Where does switch S and T, would it just look any different, or it's just kind of like?
If I switch S and T, yes. So the quickest way to do that, well, I don't want to, let's not confuse people. So let's switch S and T. And see if we can figure out what it is. And now it looks like we want T to go from, say, 0 to 2 pi, or something trigonometric like that. And S, I don't know, we could go -3 to 3. Well, let's think about it. For a fixed S, so let's think about the T parameter curves. Yeah, in fact, did I do a total switch? Which is not what you wanted, right? Is that what you wanted, Greg?
Yeah, it just,
So I get the same thing.
Yeah.
Yeah, same thing. Let me switch one variable here. Let me make that a T. Okay. So it doesn't
I was
take,
thinking of it doesn't really matter which one's S and which one's.
it doesn't, as we just saw. Okay. No, and when I thought of switching, I was thinking of this guy. So let's think about this guy. Fix an S, let T vary. Fix an S, let T vary. You've seen this curve. It's a helix. And what's the radius of the helix? S. So this is a surface whose T parameter curves are helixes. All right, let's go the other way. Let's fix a T and look at an S. They're rays, yes. They're rays emanating from the z-axis. They point in the direction cosine t sine t, and they have height t. So you can think of it, let's start at the bottom, and as I rise up it goes like this. The rays go like this. So that's what the S parameter curves do. Here's an S parameter curve, here's one, here's one. Okay, and then the T parameter curves are helixes. So there's this one, and then there's a fatter one with a bigger S, and then an even fatter one. Okay, let's see what it looks like. Oops, didn't want to do that. Now, this obviously is a limited representation of the surface, right? Because if you let S, for example, range out to infinity, then this surface goes out to infinity. So it's a really big surface, and it goes up and down, and like this corkscrew kind of thing. But look at the parameter curves, right? If you trace one of these guys up, you see a helix of radius S. And if you look at one of these guys coming out, you see a ray. Helixes and rays. All right.
Are those rays all like flat?
Yes, they are. They're horizontal, so it's difficult to see here, but
Okay.
let's go sideways here. And they are horizontal. Some people like hang these out in their porches and they blow around. They blow around in the wind. Okay. These are actually important shapes. If you go to most industrial plants that use granular raw material will have something like this on the site, because you can take this thing and shove it into a pipe and turn it, and it will lift material from a pile of stuff up to the top just by turning it. In fact, if you drive by the smelly paper plant down there at Wallula Gap, there's this massive pipe. It's probably 6, 8, 10 feet in diameter, and you can see it turning. And what that's doing is picking up wood pulp and sucking it up into the processor. And inside that thing, if you could see inside of it, would be something like that. In fact, this was one of the earliest pump designs, water pump designs. I think Romans had pumps like this. All right. We got time. What if I wanted to parameterize a sphere? Well, let's recall spherical coordinates. Something like this: rho, sine, phi, cosine, theta. Y was rho, sine, phi, sine, theta, and z was rho, cosine, phi. And you may remember that rho was positive, 0 was less than or equal to phi, was less than or equal to pi, and 0 less than or equal to theta, less than or equal to 2 pi. So this was the polar coordinate system. Sorry, spherical coordinate system. We can actually use this. The sphere of radius 1, which mathematicians would denote S2 of 1. I better put that in there just so you know the sphere. Oops. So S superscript 2 of 1 it means it's a two-dimensional sphere. So S1 of 1 is the unit circle of radius 1. S2 is the unit sphere of radius 1. S3, it's very difficult to visualize, but it's a three-dimensional sphere in four-dimensional space. And it goes right on up. Sometimes, you just need that three-dimensional sphere in four-dimensional space. So, but no, S1 is a one-dimensional sphere in two-dimensional space. S2 is a two-dimensional sphere sitting in three-dimensional space, and so on.
It's one-dimensional
described by one parameter, like theta, for example. Okay. So we can use these formulas to parameterize S2 of 1, which has a formula of its own. Right? We know the Cartesian formula for this thing, and if pressed, we could solve, say, z equals the square root of 1 minus x squared minus y squared, and that would be plus or minus there. And we could parameterize using this formula, but we only get to parameterize half of it at a time. And why settle for half when you can have the whole thing? Which is really the point of this whole exercise in parameterizations. So I can parameterize the upper half like this, or I can put a minus sign out there and parameterize the lower half, but what I can't do is parameterize the whole thing at the same time using this formula. But using these spherical coordinates, I can. So if I'm going to parameterize a sphere of radius 1, what's rho in that context? It's 1, right? I'm going to switch this around, actually. V and U. Or use spherical coordinates and let phi be V and let theta be U. And we can write R of U and V as follows. Sine V cosine U, sine V sine U, cosine V. And now with a single formula, with a single expression, we get the whole sphere. Let's plug that into the plotter and just confirm that. Perhaps play around with it a bit. I got to think about this. Sine t cosine u, sine t sine u, and cosine t. Okay, so t is playing the role of phi, u is playing the role of theta, so I'm sorry, s. So t is playing the role of phi, s is playing the role of theta, so the s parameter range should be what? 0 to 2 pi? And the t parameter range, do you remember how that worked in spherical coordinates? 0 was the north pole, pi was the south pole, and that got the whole thing, right? Okay, let's think a little bit about parameter curves. So let's think about, for example, t parameter curves. Fix an S. What's a t parameter curve? It's a line of latitude, right? It's one of the horizontal circles. So you fix a t, so now you've just got some radius here, right? Sine of t is equal, so you have some radius. Cosine s sine of s is a circle. It's a circle of radius sine t. And where is it? It's cosine t above the xy plane or below the xy plane, depends on what the sine is. Okay? So, did I say that backwards? Anyway, that was the S parameter curve. The T parameter curves, what are they? Fix an S. It's a line of longitude. And you can see that the software, that's how the software plotted it. T parameter curves and S parameter curves, latitude and longitude. Okay. You can do really cool stuff, and we saw this already, so I'm not going to belabor the point, but you can really get a very fine level of control over the surface just by restricting the range of the parameters U and V, or S and T in this case. For example, if I back off S here to just say pi, what's that going to do to the surface? Yeah, and is it gonna? How is it gonna be cut? Nick?
It's gonna be like this, right?
So it'd be like a vertical cut,
Yeah.
and then just take 1/2. Yeah. Yeah. Okay, and you can narrow. So then you can go on and narrow this guy to, like, I don't know, pi over 3. And you know, you get just a lot of control over the surface with these parameters in a way that you don't have with just a regular old z equals f of xy kind of situation. Okay. Let me show you another surface, and this will lead us into the next and final topic. What I'd like to do is build an integral that represents surface area. Now, you've already done a little bit of this in the case where z is equal to f of xy. Remember that square root of f of x squared plus f of y, f sub y squared plus 1 thing, and then you would integrate it and hope for the best. That is a special case of what you're going to see here. Let me pull up the surface and motivate what I'm about to show you. So I'm going to show you something called a torus, which is a donut. I don't know if I've showed you that before in here or not, but it's yet another surface that is very easily parameterized. Whoops. Still got my sphere in there. All right, so there's a torus, donut, whatever. And you see the parameter curves. So let me show you, this is a U parameter curve right here. So the U parameter curve just traces out a circle. And can you imagine that, right? If I took a vertical slice of this thing, what I would get would be a circle. And if I took a horizontal slice, I would get like an annular kind of region. Okay. Let me describe for you the parameters just very briefly. There are two main parameters that describe a torus. There's the radius of one of these vertical circles is little r, and then the distance from the center out to the middle of that circle is big R. And so this torus has a circular radius of 1, and then that big radius in the middle of 2. The red and the green, so these are tangent vectors to the parameter curves. So the green guy is a tangent vector to the V parameter curves, and the red guy is a tangent vector to the U parameter curves. Let me rotate that around and show you. Okay. And it's surprisingly easy to get those curves. What you do is you take the parameterization, which is right here. You don't need to, I mean, it looks similar to other parameterizations that you've seen. So this is a parameterization of the torus. And to get those tangent vectors is pretty easy. You just take the partial derivative with respect to u and the partial derivative with respect to v, and that gives you the tangent vector along a parameter curve. Why do we care? Well, let me move this guy around here a little bit. So I've got this thing set up to where, like, I don't know, let's do pi over 3. Okay, so let's look at this guy right here. And I'm going to blow this up a little bit. All right. Now, ignore the lengths of these vectors for the moment. We'll take care of the lengths. I won't completely explain the lengths, but I'll argue the lengths a little bit later. But you notice that there's this little patch of surface between the parameter curves. You have two V parameter curves here and two U parameter curves here. There's a tiny patch of surface there. And what you notice is that the tangent vector along the U direction and the tangent vector along the V direction sit right at one of the corners, one of the intersections of these things. And if you go back to the book, way back in chapter 12, the cross product section, there was an identity that I tried to draw your attention to when we were there, but it's okay if you don't remember. There was a geometric relationship between vectors and a parallelogram. And what it said was if you had a vector A and a vector B and their tails were together, they would form a parallelogram. And if you take the magnitude of their cross product, it actually gives you the area of that parallelogram. So this identity, this geometric identity that we learned so many weeks ago now, is really coming back full force. We're going to take that idea and look at the surface. So we've got this tangent vector here and this tangent vector here, and they together make a parallelogram. And that parallelogram is a pretty good approximation of that little patch of surface right there. So if we take the cross product of the green guy with the red guy and the magnitude of it, what we get is a pretty good approximation of a little patch of area right there. But you say, hey, wait a minute, these things are way too long. And you're absolutely right. This parallelogram is much too large. Right? This parallelogram is really massive. So we have to worry about how long those things should be. Now, I'm not going to argue, I'm not going to do a full-on proof about how long these guys should be. What I'm going to do is I'm going to write a formula for you. And then just try to argue why it's the right formula. So we know that the area is well approximated by a cross product. RU cross RV, like this. As long as you throw in this extra du dv thing. And these are the things that fix the length. And let me try to motivate, if not prove, why this is the right thing to do. So the area is well approximated, the area at a point is well approximated by this thing. If you go back to, oh boy, line integrals. Remember how we started out with the line integral, just this ds thing, and you remember how ds was the magnitude of r prime dt? Does that ring a bell? Okay, so that was ds. And then we wanted to compute the component of f in the tangential direction, and we did this projection thing. And if you follow the book here, and you look at this f dot r prime thing, you see this cancellation right here. And that turned into f dot tds. That cancellation let us just write r prime dt. And that same kind of thing happens when you look at r sub v and r sub u, right? Each one of them is going to get their little length vector, and each one of them is going to cancel with the d, with the area element. And that's as far as I'm going to go with that right now. So That's a very heuristic argument for why this is the right thing to study for a little patch of area. And from this, we can write the full surface area. And then you have some U0 to U1, V0 to V1, where these limits describe the region of interest. Okay. Let me just show you how this thing works in practice. So let me pull up an exercise from the book. I think I still have it marked. Boy, I'm consistent if nothing else. Yeah, number 5 is the one I wanted to talk about. So I'd like to find the surface area of this surface. The area of this surface that lies below z equals 1. I'm not going to do it, but this is one that you could have done using the techniques from earlier, right? The square root of f sub x squared plus f sub y squared plus 1, integrate that. So I'm going to do this using the parametric approach. Okay. If I have time, maybe I'll do it 2 ways. So we want okay, let's parameterize this guy. How can we parameterize this surface? You've seen me do it once already. It's pretty easy. When you have a surface that's just z equals f of xy, make x u, make y v. So if x is u and y is v, what's z? Yeah. Okay, over what set of u's and v's am I interested in this surface? Yep, u squared plus v squared less than or equal to 1. Does everybody see that? Okay, well, then I can compute r sub u, which is 1, 0, 2u, and r sub v, which is 0, 1, 2v, right? And I can compute the cross product, ru cross rv. Okay, let's do this one column at a time. So if I blot out the first column, I get negative 2u, right? If I blot out the second column, I get negative 2v. And if I blot out the third column, I get 1. Yeah? Now I don't want the cross product, I want the magnitude of the cross product. It would be, but the middle coordinate comes with a minus sign. That's okay, Sarah. I'm sure other people forgot. The magnitude of that guy is 4u squared plus 4v squared plus 1 square root, right? And the integral, the surface area integral, then, is the integral over the region, whatever that happens to be. This guy, 4u squared plus 4v squared plus 1/2 dA. this is precisely what you would have gotten if you'd used the square root of f sub x squared plus f sub y squared plus 1. The only difference is x is u and y is v now. How would you do this integral at this point? Go polar, right? Okay. I said I was going to do this 2 different ways. Let me show you a different way. Or r of u and v equals r, not r, sorry, u cosine v, u sine v. So I'm going to let x equal u cosine v, let y equal u sine v. What does that make z? U squared? And what now is the domain of u and v? U goes from 0 to 1. Come on. And v? 0 to 2 pi. It's the exact same part of the surface, just a completely different parameterization. Let's just do it again here. Ru is cosine v, sine v, and 2u. Rv is minus u sine v, u cosine v, and 0. Ru cross Rv. Okay, blot out the first column, and what we get is negative 2u squared cosine v. Blot out the middle column, and we get negative 2u squared sine v. And blot out the third column. What do we get out of the third one? Not 0. U. Right there, you get a sine squared, cosine squared in there. Okay, check that if you don't believe me. Magnitude of that guy. Okay, the magnitude of that guy is the square root of the sum of the squares. That's 4u to the 4th cosine squared v plus 4u to the 4th sine squared v, aka 4u to the 4th plus u squared square root, which is just u times the square root of 4u squared plus 1 to the 1/2. Okay, if I were going to integrate that, the surface area, I would go from 0 to 1, 0 to 2 pi, u 4u squared plus 1 to the 1/2 d u dv. How do you think that compares to the previous one? Nick?
Well, your u is going to end up 1 to 0, so it should be the same.
It's going to be exactly the same result. This integral is what you get right here. So if you do the polar coordinate transformation on that thing with the RD theta and all that sort of stuff, you're going to end up right here. Okay? I'll let you think more about that. I guess one of the things that you might be concerned about is why there isn't a UD UDV down here, maybe, or something like that. And it's just because there isn't, right? That's all taken care of in the parameterization. But it so happens with this particular parameterization, it's equivalent to doing the Cartesian version and converting to polar. But Yeah, so if you convert this guy, you're going to see, you're going to get that R, dr, d theta right there. So it's worth looking at. I didn't get a chance, I'm going to let you guys go. I didn't get a chance to talk about parametrizing planes. I'm going to briefly just point you to it. And I'll let you read it. Somewhere in here, come on. I'll just let you read it. If you have questions, you know where to find me Monday, 10 days from now. Have a great break.